All right, good morning.
Morning.
Morning. Some of y'all are not getting your name tags out. It's possible for me to learn names if we don't get our name tags out. So let's do that. All right. So we're all happy about Saturday. Yes, I was happy. I was happy. Good job. Everybody came through. So I appreciate that. Ty's not with us today, so I'm kind of flying solo. So we're gonna see how all this goes. All right. We're gonna start with like 5 minutes of discussion with each other. Then I'm gonna talk about some stuff. Okay. So here's what I want you. We're not gonna turn this in. All right, but I do want you guys to have a brief sort of discussion with your sort of immediate neighbors. Okay. So everybody remember from like the first day of class when I said look around, figure out who we think the strongest person in class is, right? And you guys put a whole bunch of stuff down and said things like biggest person who's got the most muscle, all that. That's great. Okay. What we're going to try to get into today, though, is that's not always true. Okay. That's not always true. We have up until now talked about what's the sort of cellular structure of skeletal muscle look like? How is that connected to our brain so that we can generate force and then have control of when we get that force, when we don't get that force, how does all of that work? We're going to start today, though, talking about when we put all of that together. When we put all of it together, what does that look like? Okay. How and why is Ashley stronger or not as strong as Taylor? It's not as strong as Megan and Katie and just all the way down the line. Because yes, muscle size matters, but a whole bunch of other things do too. So close your laptops, put your things down, talk to your neighbor. Okay, talk to your neighbor. Don't look forward. Don't look at this. We're going to try to get at two different things. Okay, two different things. One, right? Why, if you go and lift weights, okay, why are certain parts of the range of motion easier than others, right? If I was going to do a curl, right, be very bro-ish and I'm going to curl. As I go through this full range of motion, not every piece of it, right, is as difficult as others, right? If we're going to have to pick things up, there's a certain place in this range of motion where I'm stronger. There's a certain place where I'm weaker. Why? Second, sometimes it's easier or more difficult to pick something up versus setting it down. The external load is the same. You've got that dumbbell that weighs 20 pounds. It's still 20 pounds, right? But if you had to pick it up or you had to set it down, sometimes those things they're not going to feel the same. What I want you all to try to talk to your neighbor about, though, is why. Why is that the case? Why is it that at some places in a range of motion, it's easier or more difficult? Why is it that certain sort of up or down is easier or more difficult? And try to tie it back, okay, to structure of skeletal muscle. Because these are things that are really important. All right, I'll give you guys about 4 or 5 minutes. Go. Go ahead.
I think it's. That's video. They can be opposite. It looks like this. I started looking here. That's why. Why is it easier? Lost on that, we made it here, we made it up. I think expresses enough. I think it's for sure. You're not no longer. Active expressive platform. This one is just very.
No, I have definitely.
But that is. It's like ignoring as far as not.
Yes, yeah.
This would be.
I do, my doppelganger. Okay, okay, so when I send. So.
Ever is. You sort of need to. Yeah.
Now you find
Yeah. I like it.
Someone that's amazing, just stay below, okay. You guys can, do the,
Okay, okay, okay. Here we go. All right, here we go. We got good questions from Gavin. We got all the Avas together over here. It's interesting that many of you that have the same names have chosen to sit very near each other in that way. I think just to make my life even more confusing in that way. All right, so let's try this. Let's start with, okay, why do we think it's a situation where when I'm doing a curl, it's easier in some places, right? It's more difficult in some places through this range of motion. Who thinks they have a guess and an answer that you arrived at without cheating and looking in your PowerPoints? Because the answer is in PowerPoints. Vera, I saw your hand first, but did you put it down because you cheated?
I may have learned about it in previous class.
Learned about it, that's okay. That's all right. We're gonna bring knowledge with us. So I saw your hand first.
So
So
I
what do you think?
I think it's like an optimal length of your myosin and actin.
Okay,
And so if it's too far stretched apart, then it's harder for them to start contracting. But if they're like a little bit overlapping already, then it's easier to start the whole reaction or the whole process.
okay. Did you guys hear what Veer said? Okay. Why does, in your mind, Veer, or someone else why do you think the overlap of actin and myosin matters?
Because that's how you produce any force at all.
What do overlapping actin and myosin form? What do they form that allows us to get force?
Cross bridges.
Cross bridges, good. We always start at the cross bridge. Okay? So your first thought should be, this is critical thinking, right? Okay, I'm doing this, I'm stronger, I'm weaker at a certain place. The first thing we should think of is there something about what I'm doing that changes the number of cross bridges that I can get? Okay? Because that's where all the force comes from initially. It all comes from the cross bridges. Okay? Yeah. Veer says that the overlap matters for how many cross bridges I can get. So if you guys were to guess, okay, comparing here to here to here, where am I the strongest? Here, here, here. So 1, 2, 3. Where am I the strongest?
No.
All right. No one wants to go in for 1. Nobody wants to go in for down here. Okay, 2 and 3 are interesting for different reasons. Y'all are correct, okay? Y'all are reasonably correct. Is my muscle different? Here, here, here. Is the size of my muscle different? At 1, at 2, or at 3? Is the amount of muscle in my bicep, is the amount of actin and myosin in my bicep different? No. Good. Okay? Good. I'm going to come back to what Veer suggested in a little bit. I'll tell you that he is in a vacuum right, but functionally 100% wrong. Okay? 100% wrong. It's a great idea in theory, but it's actually not. It's not the reason that there's a difference here. Okay? In a test tube with one fiber, I can stretch one out too far. I can make them so not overlapping that you can't get cross bridges. I can make them so short that you can't get any more cross bridges and those things. But that actually is not what happens in your muscles. Okay? Right? You're here, you're not that stretched. Okay? You're not that stretched. You're here, you're not that short. Okay? So, because of some other parameters, but you're thinking about it the right way. Okay, we're thinking about it. So that's one explanation. You might have another one. Why am I stronger here? Right? Because you all know if I let you cheat and start the motion right here, you can get up with it much easier than if I made you start out all the way down here, right? Is that a child?
You're wrong.
Sorry.
Is your child working?
I don't know. Ellis would have loved to come to work. She would have loved it. It was a small child who was screaming, very upset. Did appear to be with an adult, who might have been their mom. I don't know. Anyway, just sort of parental instincts. You're like, I hear a child in distress. We must at least go check this out. Okay. Anybody else have a different explanation? Nobody wants to offer anything else. Jessica.
Is it because there's more sarcomeres in the fibers that do this instead of this?
It's a really interesting idea. It's not exactly correct. Okay. As you change the shape of the muscle, same actin, same myosin, same number of fibers, same number of sarcomeres, right? This is like physics, or I don't know, Newtonian physics or whatever, right? Like the law of conservation of, I don't know, whatever the fuck it is on all of those things. I think it's the conservation of mass, right? Also, we'll talk about thermodynamics when we get into metabolism. Energy is neither created nor destroyed. It just sort of shifts from one to the other. Your muscles are your muscles, right? In the midst of that. Okay, Tyler's been dying to say something for like 5 minutes.
Oh, is it voter recruitment? Because I know you have to have less voter, like, you recruit less to do fund then. Also too, like, if you recruit all voters at the same time, you'll like slap yourself, like hit yourself, so you have to do a couple motor neurons first, and then you increase like the, so it's like the science principle.
All of these things you're saying those are real things. These are correct things, right? But it's not exactly. So what are you suggesting is that I am unable to turn on as many motor units here as I am here?
No, your body is not turning on as many as you're right here, because if you turn them all on at the same time, you'd be constantly contracting your muscle.
But what if I want, I am trying as hard as I can to get that, to get that curled, right? I'm trying, I want all of them on. But you're saying the body won't let me, but it will let me in the middle?
No, then you just can't.
You just can't.
You just can't wrap it.
Okay, you just can't wrap it at that point, right? Okay. An interesting idea. You're hitting at something that does play a role in force generation, but it's not exactly what's going on here, but that's okay. You guys are thinking about this in the right way, right? I'm purposely being a pain in your ass to make you think, okay? Let's take the other question. Right? Is it, if I said in a vacuum, you can pick out, you got to lift the most weight possible. Is it easier to pick the weight up or to put it down? How many of you think down? Anybody in for up? Some of you are like, I don't know, I don't want to raise my hand. Also fine. So it seems like down. Why do you guys think down? Halen? Gravity. Explain.
Like gravity's like pulling your muscle like on the way down. So it's helping you rather than you fighting against gravity. Yeah.
Interesting. What is gravity?
It's a force,
It's not a force.
acceleration.
It's an acceleration. But it's still a force. I'm just being, again, I'm being a pain. It's, we measure it as an acceleration, right? It's a force. You apply the force to get the acceleration, all right, fine. Okay, right. What is gravity doing to us all right now?
Keeping us on.
Keeping us on the ground? Okay. If I give you a dumbbell and it says that it weighs 20 pounds, why does it weigh 20 pounds?
Due to the force of gravity.
Due to the force of gravity?
Yeah.
That is half correct. What does it also have to have in addition to gravity to be able to weigh 20 pounds? Ass. Good, right? So to Halo's question, to her point, okay, I'm going with it or I'm going against it. Does the dumbbell weigh 20 pounds whether I'm going up or I'm going down? So does that mean, does the mass of the dumbbell change? Does the force or the acceleration of gravity change whether I'm going up or I'm going down? No, right? It's a constant. It's constant. So it's easier if you want to make it a certain way, you want to make it easier going down, you just drop it, right? Like no force, done, false, right? But if you've got to go slowly and go down versus slowly going up or something, it still weighs 20 pounds. Okay. So I would say that you're hitting around something, but we're not exactly there. What if I said all you can pick up is 20 pounds? Do you think you can lower down more than 20 pounds? We'll do it in the same way, right? I can only pick up 20, so we know I can lower down 20, but could I lower down 25? Yeah, actually you're nodding yes. We need to try this out. I should have brought some weights. on all of this. We could like take like 7 backpacks and be like, who should curl it up? Lower it down. Do you think you can lower more weight down than you can pick up? Generally seems to be yes. Okay, why? Y'all are right, but why? Anybody other than Tyler or Veer want to weigh in? I appreciate you guys being willing, but I'm trying. Soren,
Different mechanism. On kind of improvement.
a different mechanism. Can you be more specific about mechanism?
As opposed to crossbred cycling, the engagement, it binds and it wants to bind naturally and it's just be physically off, not having or something there.
Okay, you're very close. You're very close. Okay. So the kind of contraction matters, right? When I go up with my bicep, that's a shortening contraction. When I go down, that's a lengthening or an eccentric contraction. Okay. We can always generate more force eccentrically if we need to than we ever can concentrically. And there's some things about the cross bridge mechanics that let us do all of that. Okay. So if you want to win a bet with your roommate or a friend or your boyfriend or your girlfriend or whoever, bet them, right? I can lift more weight than such and such or whatever, but just don't tell them that you're just going to lower it down, right? Like I can squat down with I probably can't squat down with 500 pounds, but you know, a lot. I'll just never be able to get back up. So that's what we want to do. Okay. Okay. So that's good, guys. That's good. What I like to do all of this because today and Wednesday, what we're going to get into is how do we control force production from your muscles? And there's a host of factors that go into all of this. Okay. And a lot of it is linked back to how do cross bridges work and connect to each other? How does that work? How does the ATPase enzymes work? Also, how does the brain signal through the spinal cord, through the motor neurons, to those muscle fibers to get those cross bridges? And then a little bit of stuff about physics, right? How does the kind of contraction that we're doing, we haven't even talked about it, but what is the speed of contraction due to different things, okay? And so we're going to dig in a little bit on all of this, and this is going to help us understand why you and your friend that are exactly the same like size, right, have different strengths, or why some people are stronger when they go faster than other people are, okay? Or why I can lower more weight down than I can ever hope to pick up. And there's some very predictable things about structure and function that are going to come into this. Okay. Okay. Now, before we jump into all of this, we need to define a few terms. We have to define the rules of the game. And I know you guys have seen all of this, so I'm going to go quickly. All right. When we talk about movements, we're going to talk about different kinds of muscles that are helping us or trying to generate this movement. Okay, so when I was using the example of a bicep curl, the biceps, or the elbow flexors, if you will, are what we call the agonists. They're the muscles that are primarily responsible for generating the force that leads to the movement. Okay, so in this example, right, we have the biceps brachii and we have the brachialis that are here that are going to cross the elbow and are going to help us sort of generate that elbow flexion. Antagonist muscles, which are probably more important than we ever give them credit for, are muscles on the other side of the joint that generate a force opposing what we're doing. So in our curl example, the triceps are the antagonists. Okay, the agonist generates force to try to pick the weight up. If we wanted to, if you want to actively push down, then the triceps can do that. But we get a thing called co-contraction. That's really, really important. Anytime you try to contract and generate force across a joint, you are going to get a contraction not only from the agonist, not only from the muscles trying to generate the movement you want, but generally you also get a contraction from the antagonist muscle. So when you're doing a curl, you're getting a little bit of force out of your triceps that are opposing the force of the agonist of your biceps and your biceps brachii. Okay, or the biceps brachii and the brachialis. Okay. So I have to generate enough force to overcome gravity and the mass, the weight of the object, plus whatever additional force the antagonist muscle is generating. Okay, so that's what's happening here. Tyler, you had a question?
Are agonists always shortening?
No. When I'm doing the down, when I'm doing the eccentric portion of a bicep curl, when I'm lowering it down, I'm doing an eccentric contraction with the agonist. So they're actually actively generating force, opposing gravity to try to lower the thing down.
Yeah, I didn't know if it was flipped.
No, I mean, it could be flipped, but it all depends on like what your intent with the movement is. If I'm actively pushing down using my triceps, that would be one thing, as opposed to resisting sort of against gravity, I'm slowing it down that way where I'm using my biceps. Okay, great question. Synergist muscles are assistance muscles. Okay, assistance muscles. They give us some level of force that help the agonist, okay, but they don't generate that much force to do a whole bunch of things. Synergist muscles create a really interesting training and rehabilitation paradigm where everyone seems to kind of go like sideways and try to understand what we're going to do. Okay. Anybody ever tried to do like squats or anything while standing on those like Bosu balls or anything like that, right? That kind of throw you off your balance. Or you've sat on a balance ball and you've done, like, say, overhead press or something there. Okay. You're taxing your postural muscles and your synergist muscles, these accessory muscles, to a greater extent when you're off balance because they got to hold you in balance. But sometimes if we train like that, we can't actually lift as much weight and do things with our agonist muscles. So what you're doing is you're sort of training the synergist, which can be useful, but it prevents your ability to maximize force production out of the agonist. And that might not be what we always want on those things. And so the idea of, I'm going to squat on a Bosu ball, great. But that's not how people that want to go to a squat competition need to train. Okay. They need to be able to maximize what they're getting from their agonist. Now, if you're me and you haven't done stuff for a while and your synergists are weak and you don't have good balance, it might actually be beneficial to try to train those a little bit first and then go do something else. So we'll get into those a little bit more so the end of this week and next week. I know you guys have seen this about the different kinds of contractions as well. Okay. Concentric contractions are where the agonists are shortening. We're getting cross-bridge cycling, the agonists are shortening. An isometric contraction, the muscle does not generally change length, at least perceptively to a person. I'm just holding the weight here. I've done a curl or I'm just holding it right like this. That would be one way. Or the wall weighs so much that when I push, I can't get a contraction, I can't shorten because there's no way for me to generate enough force to do all of that. And then eccentric is I am sort of going the direction that gravity wants me to go, but I am not letting gravity win. I'm just slowly lowering myself down. The things to understand about these kinds of contractions are that the cross-bridge mechanics are different for each one of them. And because the cross-bridge mechanics are different, the energy cost is different and the amount of force that I can get is different. Okay. And we'll put them in a hierarchy. Concentric contractions generate the least amount of force and they cost us the most energy. Okay. So if you think about what is the most weight I can curl up, if you find your concentric 1 rep max, that value will be less than what you could do isometrically, and it will be less than what you can do eccentrically. Also, for every rep that I do, I will use more energy doing the concentric than the isometric. Concentrics cost energy because the cross-bridge cycle happens. We have to attach the cross-bridge, we have to shorten, then we have to use energy to break the cross-bridge, go back, grab on again, pull again, break, back, grab, pull, over, over again. We use the energy to break the cross bridges to allow us to continue shortening the muscle. Okay, that's why they're so energetically costly compared to isometric and eccentric. Okay, we get less force because anybody ever played tug of war? Anybody ever been on like a tug of war? Few of you guys, okay? When you do a tug of war, think of cross bridges and those things as we're having a tug of war against the tendon, which is we're fighting against gravity to pick this thing up. Okay. To cycle the cross bridges and keep shortening, I have to break them. Which means if we've got everybody in the room and we're all holding on to the rope, right? We're here, but in order to pull farther, we have to let go to try to go reach down farther and pull again. As soon as we let go, as soon as anybody lets go with one hand, even, okay, we now are applying less force on the rope. And so we got to make sure to be able to go farther, we have to break, we lose force. So at any moment in time, doing a concentric contraction, you do not have as many cross bridges actively engaged as we could have under isometric and eccentric conditions. You engage all of them to start, which is kind of probably not a thing we can do, but you assume you can get them all to go. In order to keep shortening, I got to break 5% of them or 10% of them, which means now, right, I can't generate as much force, but I have to do that in order to be able to actually move and shorten the muscle. Okay, so less force in total capacity, use a lot of energy. Isometrically, because we don't change, the cool thing about isometric and eccentric is for the most part, you just engage the cross bridges and they stay there. They do not have to break. They do not have to cycle. All we want is give me force and just hold on. Okay, you're on the tug of war thing, you're on the rope and you're just there. Don't let go. Don't try to move. Just hold. Okay. Because of that, very minimal cycling. Because there's minimal cycling, you don't use as much ATP. Okay. And because you're not ever breaking them, you can engage more and you can get more force. As we'll see, isometrically, most people can get, I don't know, another 5 or 10% amount of force isometrically over what they can do concentrically. Eccentrics are a whole different ballgame. Eccentrics are strange, hence the name eccentric in that particular way. You get more force eccentrically because they're like an isometric contraction in that we don't have to cycle the cross bridges, but also you have connective tissue in the system, in the muscle, in your tendons, right? You have connective tissue. Connective tissue functions like a rubber band. You guys pull out a rubber band, right? At some point, as you stretch the rubber band, it's resisting against you stretching it out. And so when I lower the weight down, I get force from my cross bridges, but I also get a little bit of extra force from that stretching and elasticity in the epimysium, the paramysium, the endomysium, in my tendons from all of that collagen. That's resisting against the thing getting stretched out. So I can do maybe 20 or 25 or 30% more force eccentrically than I can concentrically. Okay. We do some protocols in the lab where we want to induce muscle damage. We want to make people's arms or legs sore. We find your concentric maximal strength. Then we just add 20% on and say you're just going to do some eccentric reps with 20% more weight than you can pick up one time. Just do a set of 10 or 12 or something, no problem, right? Because all the cross bridges can be engaged and we get extra force from our connective tissue. This is the kind of contractions that predominate when you go downhill, right? Your body weighs the same. Gravity is the same. So the force that I need to walk downstairs, right, where I do an eccentric contraction with my quads, is the same as when I go up those same stairs. But when I go down, it's mostly eccentric. I don't use nearly as much energy. And that's why it feels easier to go downstairs as opposed to going upstairs, or it's easier to go downhill, right? It's energetically less costly. So that is a real thing. And it all comes back to the cross bridges. It all comes back to that interaction of actin and myosin, the myosin ATPase enzyme, and what we need to do, right, in order to either get a shortening contraction, a lengthening contraction, or to hold steady. Okay. So that's why we emphasize structure that imparts function in skeletal muscle. That is why these contractions do different things and they behave in different ways. Okay. So that makes sense. That makes sense. Okay. Good. Here is a lovely experiment that was published in 1952 from a woman named Janet Meeblin Ritchie. And what they did was they had people ride bikes that look like this. So there's two bikes going the opposite direction. There's one chain. The chains are connected. So as one person pedals forward, which is a concentric contraction on one side, the person on the other bike is resisting against them doing an eccentric contraction. And so if you just ever so slightly provide resistance going backwards and let the person going forward win, if they measure oxygen consumption, if they measure energy expenditure going forward at a certain amount of work going this direction, there's this nice linear increase as work increases, metabolism goes up. Here's the same measure though in the person going backwards. So doing the exact same work or almost the exact same work going negatively, going backwards, eccentric contraction, and there's this markedly reduced ATP use, markedly reduced energy expenditure. Okay. This was one of the first experiments where this was ever observed. It's the same thing. This is going upstairs. This is going down the stairs. Okay. We use way more energy here versus there. Okay. I used to do a thing in class when I could remember to bring weights, and we would find like what we thought was right, like a big strong person in class, and we would have them do reps with a certain amount of weight, like do curls and do as many reps as you can. And then we would find a much sort of what we would agree on would be sort of a smaller, probably not as strong person. And we give them the same weight and say, okay, you're going to do eccentric contractions. Who can do more? And the person doing the eccentric contractions always win. Okay. The other thing that they did as a part of this experiment that I'm not showing is they would tell the person doing the eccentric contraction to try to win. Don't let them go forward. And they put people in that were different sizes. And what they would arrive at, right, because you're stronger eccentrically, is they could put small, less strong people doing eccentric, and they could stop the big, strong people from being able to go forward simply by the kind of contraction that they were doing. Okay. So if you want to win some money from one of your friends, you want to impress them, be like, let's do reps to failure, but I'm going to do eccentric contractions and you can do concentric ones. And the eccentric ones, they cost you almost no energy, right? And so you can do a whole bunch that way. All right. How am I doing time-wise? Oh, we're doing okay. So those are our kinds of contractions. We'll revisit that. Okay, we'll revisit that. But the other thing that we want to start with for who is the strongest, why are you stronger than somebody else? The first and most important thing for strength is just very simply muscle size. Who's got bigger muscles? Whoever has the biggest muscle probably has the greatest capacity for forming cross bridges and therefore for generating force. All other things being equal. All right. Muscles come in different sizes. They come in different shapes. Those are very much related to what is their function. Your hamstrings look very different than your quads. They perform a very different function in a lot of ways than what your quads do. If we ran backwards all the time, then the hamstrings might look a little bit different. Okay? The size, the shape, and the length of muscles help to impart function. What I, in a very general sense, want you all to appreciate is that the longer a muscle is, the more contraction velocity it can elicit, the faster it can contract. Please don't ask me to explain the physics of that. It is just so. I don't understand it. It does not make sense to me because it's physics. Okay, but that's the thing. Generally, your hamstrings can contract faster than your quads. Okay. Whereas things that have a larger cross-sectional area, okay, are going to be designed to produce force. And think of cross-sectional area as sort of this width as we look out. And I'll show you a picture of all of that. Okay. This is not a piece of steak. This is, in fact, my quad from what is way long ago now, almost 25 years ago now. Maybe not 25, maybe more like 20. Okay. This is an MRI taken as part of my doctoral dissertation, but it's taken at half the distance between the head of the femur and the top of the patella. So it's taken like right here. And what we did is the MRI takes a picture and it cuts through like this. Okay. You cut like that, and then you pull the thing up and you're looking up through my feet at this. Okay. This is a cross section. Okay. You've got the 4 knee extensors here. You've got some hamstrings down here. You've got abductors on the outside with all of that. This is bone marrow in my femur. This black space is the actual bone itself. Okay, my femoral artery is, where's my femoral artery? My femoral artery is right over here. Okay, do you see this? So the general idea is that cross section matters. So this, in theory, more cross bridges stronger than this. And then if it's even bigger still, stronger than that. All other things being equal, right? The bigger your cross section, the bigger your muscles, stronger they are. And so you can imagine, okay, great, cross section of a quad or a thigh versus the cross section of, say, a bicep. All makes sense, right? You guys are like, yep, my legs are stronger than my arms for probably a majority of you. Okay. Some bros, maybe not. We'll see. Okay. But that's the general idea. And I say it's only things where that's simple because it's really not exactly that simple. Okay. We're next going to talk about that the size matters of the muscle because it matters for how many cross bridges you have. But there's some other things and some other, we call it muscle architecture that are going to be different among muscles that also play a role on how many sarcomeres can we pack into a given amount of area. So when we talk about architecture, the thing I want you all to understand is something called pennation. Okay, something called pennation. Pennation describes the angle at which muscle fibers run or are aligned relative to the tendon that muscle connects to. Okay, so you have what are called fusiform muscles, okay, which look like this. Your bicep, in many ways, is a fusiform muscle. And so the tendon runs this way, and all the fibers in the muscle run sort of essentially parallel to the tendon. So the tendon is down here, all the fibers run like this. So when the fibers stretch or shorten, it transmits almost exclusively all of that force right onto the tendon. Okay? But you also have fibers that if here's the tendon, this is your rectus femoris, which is right here, where the fibers come in from either side and they come in at an angle. Okay? That angle is called pennation. Now, how many of you remember from physics, and please don't throw things at me, remember the idea of vectors? Okay? Of vectors. I know it's terrible, right? But pennation angles give us vectors in how we transmit force from a muscle fiber to the tendon. Okay? In a fusiform muscle, like your bicep or most of your hamstrings, right? I'm here. This is the tendon. I'm going to shorten that muscle and I'm going to pull it directly towards me. All of the fibers run exactly right in line with the tendon. So I've got like 100% force transmission. Okay, well, if it comes in at an angle, let's just say I'm over here, all the fiber can do is this. Okay, and so it pulls on the tendon at an angle. Well, that angle means, right, there's a vector that is this way, and there's a vector that is this way. Okay, and so I'm losing some force. If I want to make it move kind of forwards and backwards, I'm losing some force that's being applied horizontally. Okay. Now, this would be like a 45-degree pennation angle. Most of your muscles have nothing anywhere close to all of that. We resolve all of this by taking the cosine of the pennation angle to tell us what percentage of force is being applied in the direction that we want. I promise there's no math. We don't have to know trig. We're not going to do any of that. But what we get is when it comes in at an angle, the steeper the angle is, the more force we're losing. That's it. Okay. Most of your muscles have some pennation, which means we are not 100% efficient at transmitting force. So my question is, if we're losing force, why on earth is this a thing that we would do? There must be some advantage, or all of our muscles would be fusiform. So why have pennation? No takers? Veer.
All the activities we do are not like bodybuilder, like where you're in this perfect set position. They're like functional movements, so you have to like have more angles. You should be able to push from stuff like that.
Okay, an interesting idea. I have lots of thoughts on the idea of a functional movement versus something else, but you're not quite right. I will tell you guys, it is actually advantageous. We do this because it is to our advantage to have pennation, even though we're losing force. We find a way to use the pennation to give us an ability to overcome that loss of force, to get even more. We are stronger because we have pennation. Anybody want to guess why? What's that?
More mobile, being able to move your arms in different angles.
You're kind of getting at the thing Veer was. That's a great thought, but it's not exactly correct. When it comes down to it, Ethan?
But it increases the variability, like you can do different movements at different
It's okay. I like that y'all are thinking. Y'all are thinking about it from a movement standpoint. You're thinking about it entirely to making it too complicated. At our most basic, who is stronger? Big muscle, small muscle. Who's stronger? Okay. Having pennation lets us have bigger muscles. In the same volume of space, having pennation lets us stack more fibers in. Okay? And by stacking more fibers in, there's more cross bridges and there's more force. Okay? More cross bridges, more force. So even though not all of the force from those cross bridges gets transmitted with 100% efficiency, I can just stack in more and overcome it. Now, okay? So we'll leave it here for today. All right. Ty wanted me to remind you guys that there's a worksheet that's up. Do the worksheet. Okay. And we will see you on Wednesday. Yeah. All right. Very good, guys.
What Brian do?